Welcome to the video lecture for section 7.1. I wanted to start out today presenting you guys with a few frequently used factorizations. These are going to make our work a lot easier a little bit later on in the section when it comes to factoring larger polynomials if we can recognize some of these forms when they crop up. So the first one, the difference of squares, we've seen quite a lot. Though we haven't really stressed it very much, but that is if we have something of this form, a squared minus b squared, and a and b can be anything, then what we can break this down as is a plus b times a minus b. So for example, x squared minus 1 can be written as x squared minus 1 squared. So this can be factored as x minus 1, x plus 1, or x plus 1, x minus 1. The second form that we have seen a few times is perfect square trinomials. And these look something like one of the following, either a squared plus 2 times a times b plus b squared, which can factor as a plus b all squared, or a squared minus 2ab plus b squared, which factors as a minus b all squared. So a quick example of that might be something like x squared minus 4x plus 4. We can write this as x squared minus 2 times x plus 2 squared. So here we see that a is x and b is 2, and my middle term is minus 2 times a times b. So this can factor as x minus 2 all squared. The third factorization, which will come in somewhat handy a little bit later on, is the sum and difference of cubes. Now in this case, we are given something like a cubed plus b cubed, and this actually factors as a plus b times a second degree polynomial, a squared minus ab plus b squared. And if we had something like a cubed minus b cubed, this would factor in a very similar way as a minus b times a squared plus ab plus b squared. Now, there's a handy mnemonic for remembering exactly where everything should be with this. If you can remember the basic layout, if you have cubes, your first factor is going to involve a and b, your first and second terms that are being cubed. You'll have an a squared, an ab, and a b squared. And the mnemonic SOAP will help you to remember what the signs should all be. So if this is addition, here I have a plus, then I will have the same, the opposite, and the last sign is always positive. We can see that this works for either one, either the sum or the difference. Here with the difference, I have subtraction. So in the factored form, this sign will be the same, this sign will be the opposite, and this one will always be positive. So So we'll get you out of a bit of a jam if you ever forget what the signs on those should be. So now that we've got a couple of frequently used factorizations, our difference of squares, our perfect square trinomials, and our sum and difference of cubes, you'll probably want to jot those down and just have those handy, maybe try to commit them to memory. That will help us when we're factoring larger polynomials. Now, just to formalize the idea of a polynomial, a polynomial can be written in the following way. So all of the functions that we'll be looking at in this section are polynomials. So I'll say f of x equals, and then we'll have a leading term with a coefficient and a power of x. So we'll say that this is the highest power of x, and then from there we'll have maybe another coefficient and a smaller power of x, maybe the next smallest power. Then maybe another coefficient and the next smallest power of x. And we can have quite a few of these, so I'll truncate this and say keep doing that kind of thing till we get down to maybe another constant times x squared, then maybe another constant times x. Here we have x to the first. And finally, we might have a trailing constant with no x, or we can think of this as x to the 0 power. So this polynomial, or this structure that I'll call a polynomial, is a polynomial for n greater than 0, greater than or equal to, I should say, where n is a whole number. So the powers that we should expect to see are going to be positive whole numbers, and that's going to hold for every x anywhere in our polynomial, right? The smallest x that we can expect is x. We could have a constant, so x to the 0 power. We can have x squared, x cubed, x to the 4th, and so on, all the way up to whatever that highest power n is. Now, what we don't want is fractions. So n is never going to be a half, and n is never going to be 3/2 or a third. So let's generalize that and say n cannot be a fraction, and it's not going to be negative. Now, just a little bit of terminology. This polynomial that I have here is a polynomial of degree n. So whatever the highest power of x is, that power is the degree of the polynomial. This particular polynomial, this sort of template of a polynomial, has a leading coefficient, a sub n. So whatever the coefficient of the highest power of x is, that is the leading coefficient. We generally write these polynomials in descending order, in other words, in descending powers of x. So the highest x power will go first, then the next highest, and so on. Now, we don't necessarily see every instance of a power of x. So for example, this polynomial, let's say 3x to the 6th plus 2x squared minus 5, is a perfectly valid polynomial. All of our x's have whole number powers that are positive. Here I have 6 and 2, and I have a constant. That's also okay. But I noticed that I don't have an x to the 5th, or a 4th, or a 3rd, and I don't have an x. So I'm missing a lot of those powers in between, but that's also all right. This polynomial has degree 6 with a leading coefficient of 3. And just for good measure, the constant is also useful. So for the general polynomial, the constant is obviously the part that doesn't have an x. And in this case, our constant is the part that doesn't have an x. In this case, -5. Now a slightly different polynomial, let's call it g of x, a polynomial function 3x cubed minus 8x to the 4th plus 10x to the 5th. Now this one is not written in descending order, so we might want to rearrange it first and let 10x to the 5th come out front, and then next we would have minus 8x to the 4th plus 3x cubed. Now in this form I can pick out my leading term. That's going to give me my leading coefficient of 10 and my degree of 5. And looking at this polynomial, I notice I don't have a constant term, so I can say that my constant is 0. Now I just want to give you a quick example of a function we would not consider a polynomial, something like the square root of x plus 2. So remember, the square root is like a 1/2 power, and that's not okay. And another, maybe j of x equals x to the -2nd minus x to the -1st. These are both fractional. This is like 1 over x squared minus 1 over x. Welcome back. I would like to look briefly at the idea of long division and synthetic division of polynomials. Now, you have probably, if not recently, seen something along the lines of long division of numbers. 268. If I wanted to divide 268 by 8, I could do that using long division. Now I'll see if 8 divides 2. It does not divide 2 evenly, so I'll see if it divides 26. It does. 24 will go into 26, so 3 8s will go. And we'll subtract 24 from 26 and get 2. Now I'll bring down the 8, and I'll ask if 8 can divide 28. Well, we just saw it can divide 26. Now I can still only fit 3 8s in. So again, we'll subtract 24, and ultimately arrive at the remainder of 4. So we could express this idea using the what's called division algorithm that says that our larger number, 268, can be expressed as the product of 8 and the quotient 33 plus the remainder of 4. Now, this same idea can be used with polynomials. For example, if I wanted to divide a polynomial by x plus 2, I could divide x cubed minus 2x squared plus x minus 4. And I will perform this in very similar ways, but the difference is I will compare the leading terms to determine what I need up top, what parts of my quotient will be. So I know that x cubed divided by x is x squared. That is what I need up top. Now I will multiply my whole divisor by x squared. and subtract from what I have. So x cubed minus x cubed gives me 0, and that's by design. We're always trying to eliminate stuff on the far left. And now I have negative 2x squared minus 2x squared to give me negative 4x squared. And again, I'll bring down the x, and I can compare my leading term, in this case negative 4x squared, to my leading term in the divisor, x, giving me negative 4x, and that is what I need up top. And again, I'll take what I just found and multiply my divisor by that, negative 4x squared. Negative 4x times 2 would give me negative 8x, and I will subtract that. So negative 4x squared minus negative 4x squared, effectively plus 4x squared, gives me 0. And x minus negative 8x gives me 9x. And I'll bring down the minus 4. So last, I need to take the 9x and compare that to the leading term in my divisor, which is x. My x's cancel and I just get 9, so what I need up top is a 9. So finally, I will end up with 9x minus 18, which I need to subtract. So 9x minus 9x gives me 0, and negative 4 minus negative 18, negative 4 plus 18, gives me 14. So we see that my quotient is x squared minus 4x minus 9, and my remainder is 14. So using that same idea, I could say that the larger polynomial, x cubed minus 2x squared plus x minus 4, can be written as the product of the divisor, x plus 2, times the quotient that we found, x squared minus 4x minus 9, plus the remainder, 14. And that is how long division of polynomials is going to work. Now there are a few details that we need to watch out for. For one thing, in the polynomials that we did in this example, we had every power of x. We had a constant, an x squared, and an x cubed. And in our divisor, we had a constant and an x. Now that has to happen. You always have to have something in every slot. You have to have a representation for every power of x. So for example, if I wanted to divide x cubed plus x minus 1 by the polynomial x squared plus 2, my division would require me to supply an x squared for the first polynomial and an x term for the second polynomial. So what that would look like is my divisor out front would be x squared plus 0x plus 2, and my dividend, x cubed plus 0x squared plus x minus 1. So I had to supply something to occupy the x space in my divisor and the x squared space in my dividend. If you're ever missing a term, if you are missing an x or an x squared or an x cubed, you have to supply it. So where to go from there? We'll compare x cubed and x squared. So I need an x up top. And if I multiply everything by x, I will get x cubed plus 0x squared plus 2x, and if I subtract all of that from what I have, my x cubes are gone, my x squareds are gone, and my result is merely x minus 2x negative x. And I'll bring down the minus 1. Now I am actually done at this point because the degree of what I ended up with is smaller than the degree of my divisor. So my quotient function is just x, and my remainder function is negative x minus 1. Now in the next video we'll see a slightly shorter, if more abstract, method for performing division of polynomials under special circumstances. So generally speaking, long division, as we saw in both examples, is going to be the most effective method. But in the next video we will see what's called synthetic division, which does help us in a lot of cases and will help us quite a bit in this section. So in the last video we saw long division of polynomials, and that method will work to divide any polynomial by any polynomial of a smaller degree. But in the special case where the divisor is linear, that is, if we are dividing by something like x minus c, then we can use a technique called synthetic division. So I will use both approaches simultaneously. I will divide one polynomial, let's say x cubed plus 6x squared minus 9 by x plus 1. So our approach with long division, we have x plus 1 outside, and under the division sign we'll have x cubed plus 6x squared. We're missing an x term, so I'll put a 0 there, minus 9. And our approach with synthetic division is to set up a little box in the top left side, and in that box I am going to put negative 1, since what I am dividing by is x plus 1, this is x minus negative 1. So we're always going to take the opposite of whatever we have in our linear divisor. Now along the top row I'm going to put the coefficients of my dividend. So I have a 1 for the x cubed term, a 6 for the x squared term, a 0 for the x term, and a negative 9. Alright, so I'll perform the long division first. I'll compare x cubed and x. I need an x squared there. So x cubed plus x squared. And I subtract the stuff on the bottom, so x cubed vanishes, and I just get 6x squared minus x squared, 5x squared. Bring down the 0x. I'll compare again, 5x squared to x, I need a 5x. And I'll multiply my divisor by 5x. And subtract. So my 5x squareds cancel, and I have 0 minus 5x. And I'll bring down the negative 9. And finally, compare my negative 5x to x. I need negative 5. Multiply negative 5 times my divisor, negative 5x, minus 5, which I must then subtract. And my x terms will vanish, and I'll have negative 9 minus negative 5. So negative 9 plus 5 gives me negative 4 as a remainder. Okay, so we have our quotient function, x squared plus 5x minus 5, and our remainder is negative 4. Now with synthetic division, the process is much more concise. So first, what I'll do is bring down the first coefficient. Then I will multiply the coefficient times the number in the box, and put that right here. Then I will add this column. 6 minus 5 would give me, or 6 minus 1 would give me 5. And now I will multiply the result 5 times what's in the box. And again, I will add 0 minus 5 now gives me negative 5. And I'll multiply one more time, negative 5 times what's in the box. And finally add my last column, giving me negative 4. Now, the three numbers that I have circled here are the coefficients of the quotient function, and this final number is my remainder. Now, when I divide a cubic function by a linear function, the result is going to be one smaller power of x. So a cubic will leave me with a quadratic. So I can tell that this quotient function will be x squared, coefficient of 1, plus 5x, coefficient of 5, minus 5. And that's exactly what we came up with using long division. So let me try one more of those. Let me divide x to the 7th plus 2x to the 6th minus x to the 4th plus x squared minus 2. I want to divide this by x minus 2. So I will use only synthetic division this time. This is a very large polynomial I'm dividing, so long division would get very expansive, take up a lot of space. But synthetic division is only ever going to take up 3 lines. So in the box I will put 2, because that is the opposite of what I have in my divisor. Alright, I'll have a 1 as a coefficient of x to the 7th, a 2 as a coefficient of x to the 6th. I'm missing an x to the 5th, so I'll put a 0 there. I have negative 1x to the 4th. I'm missing an x cubed, so there's another 0. I have 1x squared. I'm missing an x, so one more 0, and a negative 2. So we'll use exactly the same procedure. I'll bring down the 1, multiply. I'll add these guys, and multiply. I'll add these guys, and multiply. I'll add these, and multiply. Add again, and multiply. Add again, and multiply. Add again, and multiply. And finally arrive at my remainder of 242. My remainder is always going to be the last number, and then working my way from the right, this will be my constant, my x term, my x squared term, my x cubed term, my x to the 4th term, my x to the 5th term, and finally my x to the 6th term. So quotient function, if I divide this 7th degree polynomial by this linear polynomial, I will arrive at a 6th degree polynomial with a remainder of 242. So we can see how nice synthetic division is in terms of dividing one polynomial by a linear polynomial. So this is a nice way of answering the question, is a function f of x divisible by x minus k, by a linear factor? Now, when we factor polynomial functions, we like to try to factor it into linear factors. So for instance, x squared minus 4x plus 4 can be factored into x minus 2 times x minus 2. So if a factor divides a polynomial evenly, that is, if we get a remainder of 0, then we could say that that factor is one of the factors of the polynomial. One of our main goals is going to be factoring polynomials, so being able to quickly determine whether a linear factor is a factor of a polynomial is going to be of great use to us. Late in the chapter, in the text, we are given the remainder theorem, which states that if r is the remainder of dividing a polynomial by a linear factor, then evaluating our function at the constant in that linear factor would result in the remainder. So an application of this would be to determine what is f of negative 2 if f of x is the polynomial 5x to the 4th minus 3x cubed plus x squared minus x plus 9. Now there are two ways we could figure this out. We could plug negative 2 in, raise it to the 4th, cube it, square it, and perform the calculations. But we've just gotten a very quick tool that would allow us, using the remainder theorem, to perform this calculation much more quickly. So if we plug negative 2 in, we would arrive at the same result as if we divided our polynomial by x minus negative 2. Now, that is the same thing as dividing by x plus 2. So I will perform synthetic division using that linear divisor. So I'll put negative 2 in the box, and I'll bring down all the coefficients of this polynomial. So 5, and I'm missing a couple of terms. Well, no, just, actually I have everything. So 5x to the 4th, negative 3x cubed, 1x squared, negative 1x, and 9. And I will perform synthetic division just as we have up till now. Bring down the 5 and multiply. Add my column, negative 3 minus 10 would give me negative 13, and multiply, giving me 26. If I add these, I get 27, and if I multiply 27 by negative 2, I will get 54 negative. So negative 55, and I'll multiply one more time, giving me 110, and if I add, I find my remainder is 119. Now I don't actually care about the quotient function, all I care about is the remainder. So if my remainder of performing synthetic division, in other words dividing my function by this linear factor, is 119, this is exactly the same as evaluating my function at negative 2. So you can plug this into your calculator, plug negative 2 in for x into your function, and make sure that this works. But this theorem says that it will always work. So you can now use synthetic division to evaluate functions at particular x values. Now, the reason that this works, if I were to divide f of x by x minus k, then I would arrive at a quotient function and a remainder, and I could write f of x as x minus k times my quotient function plus my remainder. So, if I plugged in k, then I would evaluate my function written in these terms as k minus k, q of k, plus my remainder, and k minus k gives me 0. So ultimately, this entire piece is just 0, and so f of k is equal to my remainder. In the case of the example we just looked at, our polynomial, f of x, 5x to the fourth minus 3x cubed plus x squared minus x plus 9, once we perform synthetic division, could be written as x plus 2 times the quotient. Now I see my quotient is 5x cubed minus 13x squared plus 27x minus 55. Plus my remainder, 119. Now, if I plug in negative 2, that would be negative 2 plus 2 times 5 times negative 2 cubed minus 13 times negative 2 squared plus 27 times negative 2 minus 55 plus 19, or 119. And this piece is 0. So I'm multiplying 0 times all of this complicated stuff. So all of that ends up being 0, and I just get 119. So this demonstrates how powerful the remainder theorem is. As soon as we have synthetic division and the remainder theorem, we can pretty much evaluate any polynomial function at any x value much more quickly. In the real number system, it means if one number is a factor of another, it means that it divides it evenly. In other words, if I were to divide 2,186 by 2, I would be able to fit 1 2 in, and get 0, bring down the 1, and the 8, since 2 does not divide 1 evenly, I can fit 9 in, and I get 0 left over. Finally, bringing down the 6, I can fit 3, and my remainder is 0. So we know that 2,186 is an even number and therefore is divisible by 2, and we are confirmed in our suspicions by arriving at a remainder of 0. The same is true with polynomials. For example, x minus 1 dividing x squared minus 1. So let's add an x term. I would need an x, so x squared minus x. Subtract all of that. X squareds disappear, and I have 1x left over, bringing down the negative 1. And I need 1 for the remainder of 0. So we have just proven that x minus 1 is a factor of x squared minus 1. When we divide x squared minus 1 by x minus 1, we get a remainder of 0. So, if we combine this idea with the remainder theorem from the previous video, we get a very powerful result. Recall that f of k is equal to the remainder if we divide f of x by x minus k. So, if f of k equals 0, then the remainder of dividing f by x minus k is 0. So, x minus k must be a factor of the function f of x. That is the factor theorem. So, this is a double-edged sword. This says if we plug in k and we get 0, in other words, if k is a 0 of the function f, then x minus k is a factor, and vice versa. If x minus k is a factor of our function, then k is a 0 of the function. K, when evaluating in f, gives us 0. Now, we've seen this going one direction before. If I wanted to find the zeros of f of x equals x squared plus 4x plus 4, I would set the function equal to 0 and then factor. And see that x equals negative 2 is my 0. And that's because x plus 2 is a factor of this polynomial. In fact, it's the only factor. This 0 occurs twice. But, as we said, this sword cuts both ways. So if I asked, is x plus 2 a factor of our function f of x equals x squared plus 4x plus 4. Now this function is manageable. We could factor it and see if x plus 2 makes an appearance, but our factor theorem says that x plus 2 is going to be a factor if and only if f of negative 2 is 0. Alright, so we can either perform synthetic division, try to divide f of x by x plus 2 and see if it divides evenly, that is, see if we get a remainder of 0, or if it's more efficient, we can evaluate f of negative 2, and remember that evaluating our function will give us exactly the same result as if we found the remainder by dividing our function by that linear factor. So f of negative 2 is negative 2 squared plus 4 times negative 2 plus 4. That is 4 minus 8 plus 4. So since f of negative 2 equals 0, x plus 2 is indeed a factor. We already knew that, but this kind of illustrates how this will be useful later on with larger, more complicated polynomials. Here we see another example, very similar to the last one that we looked at. We are asked, is x plus 4 a factor of this third-degree polynomial x cubed minus 13x plus 12? Now, this function is one that we are not very well equipped to factor. So we are a little bit stuck. I don't know how to factor this, so I'm going to have to use another approach rather than factoring and seeing if x plus 4 shows up. So we have two choices. We can use synthetic division, divide this function by this linear factor. Actually, we could use long division, but since this is a linear factor, synthetic would be much quicker. I can divide this by putting -4 in the box. I'll bring down all my coefficients. I have an x cubed. I don't have x squared, so I'll put a 0 there. Minus 13 plus 12. Don't really need the plus. And our procedure is nice and quick. If I bring down the 1, multiply by what's in the box, add, multiply by what's in the box, add, multiply by what's in the box, and add, I see that I get a remainder of 0. So we can conclude that yes, x plus 4 divides x cubed minus 13x plus 12 evenly, and is therefore a factor. Now another way of doing that, we could have evaluated our function at -4, and we would arrive at the same result. So f of -4 is -4 cubed minus 13 times -4 plus 12. Now this might be a little bit more work. -4 cubed is 64, -64. 13 times 4 is 52. And I do in fact end up with a result of 0. So this fact that f of -4 equals 0 implies that x minus -4, in other words, the factor we are interested in, is a factor of the polynomial f of x. In fact, my polynomial can be written as x plus 4 times the quotient. Remember, the synthetic division tells us the quotient is x squared minus 4x plus 3. And we could go so far as to factor the remaining quadratic factor as x minus 3, x minus 1. So finding one factor allowed us to factor the function completely. Welcome back. So polynomials, just like exponentials and logs, are a family of functions which share a lot of the same features. Now there's one theorem which applies to all polynomials, and it says if you have a polynomial of degrees, say, n, so n could be 1 or 2 or 17 or 86, any positive whole number, this polynomial will have a maximum n zeros. In other words, its graph will have n x-intercepts at most. Now, what this tells us is if I have a polynomial of degree 4, and I find 4 x-intercepts, 4 zeros for that polynomial, then I'm done. I found them all. I can only ever expect to find 4. We've seen this idea in practice before when we talked about polynomials of degree 2, say f of x equals x squared plus 4x plus 4. If we wanted to find this polynomial function zeros, or x-intercepts, we would set the function equal to 0, and then work towards solving for x. Now this is a quadratic, so this polynomial, we should see if it factors, you'll notice that this is a perfect square trinomial, so I can factor this as x plus 2, x plus 2, in other words, x plus 2 quantity squared. So if that's equal to 0, this implies that x plus 2 equals 0, so x equals negative 2. So this particular polynomial has one 0. And that's okay. We're allowed to find 1, we're allowed to find none. And we have seen that in the past. The only restriction is that we're never going to find more than 2. Now, closely related to the idea of zeros is the idea of multiplicity. So every 0 of a polynomial has a multiplicity associated with it. And just to formalize what that is, the multiplicity of a 0 and I should say the 0 of a polynomial, the multiplicity is exactly the number of times that 0 occurs as a root of the polynomial. Now, that's a little bit of a strange definition. To make some sense of it, let me give you an example. So suppose we have a polynomial f of x. Actually, let's use the one that we just saw. F of x equals x squared plus 4x plus 4. Now, another way we could write this in its factored form would be x plus 2 quantity squared, and we already saw that x equals negative 2 is the 0 of this polynomial. Now, this result only gave us one 0, the 0 being x equals negative 2. So we look to the power to tell us the number of times that this 0 occurs as a root of this polynomial. So the multiplicity of this 0 is 2, since it occurs twice. In other words, the number of times that the factor that gives us a 0 shows up in the factored representation of the polynomial, that will also tell us the multiplicity of that 0. So a little bit more complicated example. Say g of x equals x minus 1 quantity squared, x plus 2, x minus 3 quantity cubed. So if you were to multiply this whole polynomial out, you would see that it is a 6th degree polynomial, and I will explain why I know that in just a moment. So at the moment, it's in factored form, so if I were to set this polynomial equal to 0, then each one of these terms being 0 would satisfy this equation. Or terms rather, factors. So this factor of x minus 1, this is 0 if x is 1. This x plus 2 factor is 0 if x is negative 2. And this third factor, x minus 3, is equal to 0, thereby satisfying the equation only if x equals 3. So here we find all of the zeros of the polynomial. We found 3 of them. And to figure out what each of their multiplicities is, I'll call it m, I'll just look at the power of the factor which gave us that 0. So x equals 1, we arrived at that by looking at this first factor, which has a power of 2. So this zero's multiplicity is 2. Our second 0, x equals negative 2, the second root of this polynomial, came from a factor which only showed up once. We have an implied power of 1 on that factor. So this zero's multiplicity is 1. And our last 0, x equals 3, came from this third factor, which occurs 3 times in the polynomial. So its multiplicity will be 3. So you can see that every single 0 has a multiplicity associated with it. If a number is a 0 of a polynomial, and that factor that gave it to us occurs 2 times, then its multiplicity is 2. If the factor which gave us that 0 only occurs once, then it has a multiplicity of 1. So the smallest multiplicity we can expect to find is going to be 1. In the next video, I will return to this polynomial that we were just working with and explain exactly how we can figure out what its degree is. In this form, our function is factored, so we don't have that leading term and power of x sitting there waiting for us to pick out that information. We would have to multiply out this entire polynomial. Or we can be a little bit sneaky, and I'll show you in the next video how we can figure out what this leading term would be without necessarily having to do too much work. So as promised, we were looking at a function last time, g of x equals x minus 1 squared times x plus 2 times x minus 3. Now, we are often interested in both a polynomial's zeros, in other words, its x-intercepts, but we're also interested in the degree of the polynomial and the leading coefficient, as well as the constant. So to find those in this case, we would want to know what is the leading term. In other words, if I were to multiply all of this out, what would the leading term be? What would the leading coefficient be? And what would that power of x be? So I'll start small. I'll multiply x minus 1 times x minus 1. And then the rest of the polynomial is x plus 2, x minus 3, and I'll space this out so we can see what we're doing. I've got 2 x minus 1s and x plus 2 and 3 x minus 3s. So if I multiply x plus 1, I'll get, or x minus 1, I'll get x squared minus 2x plus 1. And if I multiply these second two factors together, x plus 2, x minus 3, I will find, and I'm doing all of this by foiling, x squared minus 3x plus 2x would give me minus x, and 2 times negative 3 would give me negative 6. And finally, if I multiply my third pair of factors together, I would get x squared minus 3x minus 3x, so minus 6x. And then negative 3 times negative 3 would give me positive 9. So we're making progress. Now, multiplying out these factors is going to be a little bit more work. Now, we get lucky when we're multiplying linear factors together. We can FOIL, as we just saw. But when I have anything bigger than that, I need to use the distributive law very carefully. So, the first thing I'll do is multiply these two factors together. So I'll multiply x by everything in the second factor, or sorry, x squared. My first term times x squared minus x minus 6. And then I'll multiply negative 2x times x squared minus x minus 6. And then I'll multiply 1 times all of that stuff, x squared minus x minus 6. Alright, and remember all of that is eventually going to be multiplied by x squared minus 6x plus 9. So if I distribute that x squared, I'll get x to the 4th minus x cubed minus 6x squared. If I distribute the negative 2x, I'll get negative 2x cubed plus 2x squared plus 12x. And I still have x squared minus x minus 6. Alright, so before I go using the distributive law again, I'm going to clean up this big first factor. So I can't combine the x to the 4th with anything. I only have one of those, so I'll keep him. Then I have minus x cubed minus 2x cubed, and that seems to be it. So minus 3x cubed, and I'm done with those. And now I'll look at my x squareds. I have minus 6x squared plus 2x squared plus x squared. So altogether, negative 6x squared plus 2x squared would give me negative 4x squared, plus x squared would give me negative 3x squared. And we're done with those. Then I have a couple of x terms. I have plus 12x minus x, so plus 11x. And finally I have a constant minus 6. Okay. So finally, if I distribute, I think I'll distribute this factor in. I'll multiply each of the terms in my smaller polynomial by the larger polynomial. So x squared is going to get multiplied by x to the 4th minus 3x cubed minus 3x squared plus 11x minus 6. And negative 6x is also as is 9. Alright, so finally, if I distribute all of those coefficients, as you will, into these larger polynomials, my first set will give me x to the 6th minus 3x to the 5th minus 3x to the 4th plus 11x cubed minus 6x squared. And we're done with that piece. My second line will give me negative 6x times x to the 4th, negative 6x to the 5th, negative 6 times negative 3 plus 18x to the 4th, plus 18x cubed. Let's see, 11 times negative 6 would be minus 66x squared. And negative 6 times negative 6x would give me plus 36x. And we're done with that guy. And finally, the last line, I'll multiply 9 times everything. So 9 times negative 3x cubed would be 27x cubed. 9 times negative 3x squared, negative 27x squared, plus 99x, minus 9 times 6, 54. So So finally, we have actually performed the whole multiplication. All we need to do is gather like terms and simplify. So I have an x to the 6th, and then I have some x to the 5ths, negative 3x to the 5th, and negative 6x to the 5th. That gives me negative 9x to the 5th. I have some x to the 4ths. There's negative 3x to the 4th, plus 18x to the 4th, plus 9x to the 4th. So, grand total of 1524 x to the 4th. And then our x to the 3rds, 11x to the 3rd, 18x to the 3rd, negative 27x to the 3rd will give us positive 2x to the 3rd. And x squared, we have negative 6 minus 66 minus 27. So negative 99x squared. And I have x's, 36x and 99x gives us 135x minus 54. So this is our final polynomial. We have a leading term of x to the 6th and a leading coefficient of 1. So our degree is 6. And just for good measure, our constant is negative 54. Now, in the next video, I will show you exactly how we can find all of this information without using an entire page to multiply out the whole polynomial, because we have a lot of stuff in the middle that we don't care a whole lot about. So we saw in the previous video that this polynomial, g of x, is very tedious to multiply out and write as a standard polynomial in the descending powers of x. So a little shortcut here is to look at the highest power of x in each factor and raise it to whatever power is acting on that factor. So in this case we have x, and I'll square it. And here I have x to the 1st, and I'll raise it to the 1st. So I'll multiply that by x. Here I have x, and I'll cube it. So our leading coefficient, our leading term will be x to the 6th. And we can do the same kind of thing with our constants. So here I have negative 1, and I am raising it to the 2nd power, so negative 1 squared. Here I have 2, and I'm raising it to the 1st power. And in this 3rd term I have negative 3, and I am cubing it. So negative 1 squared gives me 1, times 2 times negative 3 cubed, that would be negative 27. And if we multiply all of that out, we get negative 54. So since, as we'll see, most of what we care about with a polynomial comes from its leading term and its constant, this type of shortcut is very helpful. Let's see another example. So if I have a function f of x equals x squared plus 1 squared times x minus 3 squared, I would like to know, if I multiplied this all out, what would my leading term be? So I'll look at the leading term inside of each factor. So my leading term in the first factor is x squared, and I'll square that. My leading term in the second factor is x, and I'll square that. So finally, if I square x squared, I can write that as x to the fourth. And if I add those powers together, I get x to the sixth again. So this is also a sixth degree polynomial. So our leading coefficient is 1, and the degree is 6. And we can do the same kind of trick for our constant. So 1 squared would be 1. And negative 3 squared would give me 9. So 1 times 9, my constant is 9. And you can do the same type of trick even if you have coefficients. So if h of x equals 2x squared minus 5 squared, x minus 3 squared, then I'll take my leading term and raise it to the applicable power. So that would be 2x squared, all squared, times the next factor's information. So I'll take x and I will square it. So if I square 2x squared, I square the 2, giving me 4, and I square the x squared, giving me x to the fourth. All of that still times x squared, so ultimately we get 4x to the sixth. So our degree of this polynomial h is again 6, and our leading coefficient is 4. And we can do the same kind of thing with the constants. So I'll take the negative 5 and square it, and multiply that by the negative 3 squared. So 25 times 9, giving me a constant of 225. Welcome back. We've recently seen how to find zeros using several techniques, and how to determine their multiplicity. So why do we care? Well, it turns out that a zero's multiplicity can tell us a lot about what the graph does at that point. So if we have a function f, and we find a zero of that function, say k, if k has even multiplicity, the graph of our function will effectively bounce off of the x-axis. At that point. In other words, if my function is above the axis to the left of x equals k, it's going to be above it again to the right. So it'll pass through k comma 0, but it'll stay on the same side of the x-axis. On the other hand, if we are looking at a zero that has odd multiplicity, then our function's graph will actually cross the x-axis. I'll say cross because it does in fact touch, even if the multiplicity is even, but it will jump from one side to the other, either going from negative to positive or positive to negative, at x equals k, at that zero, that x-intercept. So a couple of examples. We'll look at just a simple one. Say one function f of x equals, and I'll give it to you in factored form, x minus 2 all squared. We know this has a 0 at x equals 2, because x equals, or x minus 2 is a factor, so we can tell that x equals 2 will be a 0 by the factor theorem. And looking at the number of times that that factor appears, we can tell that this has a multiplicity of 2 also. In other words, we have an even multiplicity. So our function, we could graph this using transformations of basic functions. This is our basic x squared shifted to the right 2 units. But it's just a polynomial, so we can talk about polynomial type information instead. So we have a 0 at x equals 2. We're going to hit the x-axis. And I see that I don't have a negative here, so my polynomial will open upwards. So from the left, it'll come in and hit the x-axis right at 2, and then bounce back off and keep going up as we proceed to the right. So a slightly different example, if I have g of x, and again we'll use a factored function, x plus 3 all cubed. We could graph this again as a transformation of a basic function. This is x cubed, and we're going to shift it to the left 3 units. But as it stands, I see that x plus 3 is a factor. So, by the factor theorem, x equals negative 3 is a 0. In fact, since x plus 3 is really the only factor, x equals negative 3 is really the only 0. And it has a multiplicity of 3, since there are 3 occurrences of that factor. So if I plot that x-intercept at negative 3, I know by the multiplicity being odd that this function is going to cross the x-axis. And using a little bit of additional information, this will be explicit a little later in the section, but right now I just know this is going to look like x cubed, so I know it goes down to the left, so it's always increasing, and we hit the x-axis and then we keep going from there. So you can see how we cross from the negative side to the positive side right there at that x value of negative 3, at the 0, which has odd multiplicity. So as you can see, these polynomials that we are dealing with here act similar to quadratics, right? They are only ever 0 at their x-intercepts. So anywhere else, they're either positive or negative. And since their domain goes on forever, we can see that there are intervals where it'll be positive and intervals where it'll be negative. So that's going to come in handy in 7.3. For right now, let's look at one more of these. Say I have a function f of x equals x cubed minus 1. So I would like to work towards graphing this thing. I will find all of its zeros and their multiplicities. So remember back to those preliminaries, this is a difference of cubes, even though it's kind of masquerading as something else. Since 1 is its own cube, is its own square, we can always do this trick of saying 1 is 1 cubed. And then I can factor this as x minus 1. Remember, we're going to have the same sign. And then x squared, opposite sign, x times 1. And then our third sign is always positive, so we'll add 1 squared. So our factorization, x minus 1, x squared plus x plus 1. And now in this second piece, the second factor, we could try to factor that further. We're not going to get very far. You could use the quadratic equation. If we were setting this equal to 0, we would see that x equals 1 is a 0. And we can see that it has a multiplicity of 1. Now looking at the other piece, say x squared plus x plus 1, when is that equal to 0? Well, we can use the quadratic formula and say x has to be negative 1 plus or minus the square root of 1 squared minus 4 times a times c. And funny looking as it is, this quadratic has coefficients of 1 everywhere, so it's kind of nice. So negative 1 plus or minus the square root of 1 squared minus 4, negative 3, all over 2. So we see there are actually imaginary roots, negative 1 plus or minus root 3i over 2. And each one of these occurs once, so they also have multiplicity, but we can't plot these. So we only really care about the real zeros that we come up with. So real numbers that we can plot on the xy plane. And my best guess as to what the graph of this looks like is it's probably going to look like x cubed. Pretty similar, right? In fact, I know that this is the graph of x cubed shifted down 1 unit. So, if I plot my 0 at 1, I know my graph is going to cross only in that one place. So finding these zeros is a powerful tool towards helping us to graph these functions, but as always, there's more to it than just the x-intercepts. We can find the y-intercepts and some other features of the graph that we'll talk about a little bit later on. Welcome back. We've talked about polynomials as a family of functions, and this family has a lot of features in common. For instance, given any polynomial with any degree, say n, the domain will be all real numbers. They're going to extend in both directions horizontally forever, and there's no x value that you cannot plug in. In talking about features of graphs, we've mentioned turning points before. Remember, those are local maxima or minima. Now, a polynomial of degree n will have at most n minus 1 turning points. And we've already said that this polynomial, this hypothetical polynomial of degree n, will have at most n real intercepts. And it could have less. Now it will have n real or complex x-intercepts, so you never need to look for more than n zeros, that is, setting our function equal to 0 and solving. But these real intercepts will have either even or odd multiplicity. Now finally, we'll talk about the overarching picture of our polynomials, and every polynomial will have n behavior falling into one of the following 4 categories. So if our degree is even, or if our degree is odd, we will see 2 different types of behavior. And if our leading coefficient is positive or negative, we'll see 2 different types of behavior. So the graph of the polynomial with an even degree and a positive leading coefficient will behave somewhat like the graph of a basic polynomial that we've seen, x squared. In other words, somewhere in the middle, we can say our polynomial may be doing very interesting stuff, but ultimately, it will open upwards. So as it goes off to the right, the end behavior will be increasing, and as it goes off to the left, our graph will be traveling upward as well. Now, if I have an even degree polynomial with a negative coefficient, just like negative x squared, this function will ultimately open downward, so we'll point down on both sides. On the other hand, if we talk about polynomials with odd degree, we can think of ones that we've seen before, like x cubed. And if x cubed has a positive leading coefficient, then it travels upward to the right and downward to the left. So our end behavior will resemble this graph. And if x cubed has a negative leading coefficient, that will be flipped, and we'll go down to the right and up to the left instead. So this is why we cared so much about the degree and the leading coefficients of our polynomial. We can tell a whole lot about the overall graph just using those two pieces of information. So for example, we'll use all of that to graph a polynomial. So just a little bit of procedure, some advice on information that you'll want to find in terms of graphing polynomials. First, we would probably want to find the y-intercept. Remember, finding the y-intercept is usually the easiest thing that we can do. Once we know that, we can determine the end behavior. And we can find all of the zeros and their multiplicities. And remember, the evenness or oddness of the multiplicities will determine whether the graph bounces off or crosses at those x-intercepts. And finally, we might just plot a few additional points in between all of these that we've already found, and then connect up using a smooth curve. So let's get a little bit of practice with that. We will graph a polynomial in its factored form. So here we have a polynomial given as a collection of factors rather than multiplied out. So the first thing we can do, and no matter what form your polynomial is in, you can always pretty easily find the y-intercept. Remember, you will plug 0 in for x. And we're plugging it into this, so we'll have 0 minus 2 squared, 0 plus 3, and 0 plus 1 squared. So if I simplify that, negative 2 squared gives me 4, 3 gives me 3, and 1 squared gives me 1, so our y-intercept will be at 12. 0, 12. Okay. Now the second thing that we would like to do is determine the end behavior. And in order to do that, I need to know what is happening with the leading term. Remember, the leading term is where I will figure out what the leading coefficient is and what the degree is. Both of those are necessary to determine what the end behavior is. Remember, the degree tells us whether the polynomial opens up or down, whether the polynomial goes up in both directions or down in both directions, or if it alternates, if it goes up to the right and down to the left, or down to the right and up to the left. And then the leading coefficient will tell us which of those choices we need to choose. So we'll go back to that trick from previous lectures and look at each of the leading terms within each factor. So I will take x and square it, and I will take x and raise it to the first power, and I will take x and square it. So in all, I end up with x to the fifth. So we have a degree of 5 and a leading coefficient of 1. So we have a positive leading coefficient and an odd degree, which tells me my end behavior will look something like this. Now, once we know the end behavior, we want to find all of the zeros. And that is going to require us to set our function equal to 0. So if 0 equals x minus 2 squared times x plus 3 times x plus 1 squared, then I have 3 options. If x minus 2 equals 0, that's because x equals 2. If x plus 3 equals 0, that's because x equals negative 3. And if x plus 1 equals 0, that's because x equals negative 1. So each of these zeros has a multiplicity associated with it. The multiplicity of our first comes from the number of times that factor appears. And the multiplicity of x equals negative 3 is just 1. There's only one of those. And our multiplicity for x equals negative 1 will be 2. So every time I have an even multiplicity, our function will bounce. And I have 2 cases like that. And I have an odd multiplicity at x equals negative 3, so my function will cross at x equals negative 3. So let me plot all of that information. Alright, I will plot my y-intercept first at 0, 12. And I'll plot all of my x-intercepts at 1, 2, negative 3, and negative 1. Alright, remember my end behavior, just in the back of my mind. I'll say my function will go down to the left and up to the right. And now, using all of the information that I have, I can actually get a pretty good graph of this function. But just for the sake of accuracy, let me plug in some x values in between the ones that I know about. So let me try, let's say, x equals negative 2, and see what y would be, what the point would be when x equals negative 2. So my function is negative 2 minus 2 squared, negative 2 plus 3, negative 2 plus 1 squared. That would be negative 4 squared, 16. Negative 2 plus 3 gives me 1, and negative 2 plus 1 gives me negative 1, which I square. So my function will be at a height of 16. So if I plot the point negative 2, 16. And if I plot another x value, say x equals 1 in between my y-intercept and the 0 on the far right, plugging in 1 would look like 1 minus 2 squared, 1 plus 3, and 1 plus 1 squared. So negative 1 squared would be 1, 1 plus 3 would be 4, and 1 plus 1 squared would be 2 squared, which would also be 4. So we also get 16 as an output when x equals 1. So the last piece of the puzzle is just to connect up. Now remember, I'm going to cross at negative 3, so from below I will cross, come all the way up and hit negative 216, come back down, and I'm now going to bounce off of my 2 remaining zeros. And continue going up forever. So this is as good of an approximation as we can get. You'll get better tools for getting your graphs to look exactly right if you pursue a calculus course, but these are all of the data that we are going to be using. So we can answer a lot of questions and graph polynomials now based on those facts about this family of functions, as well as the procedure outlined in the previous videos. But we can answer some slightly more interesting questions as well. For instance, if I am looking at the graph pictured here, I can make some inquiries. I can see what is the smallest possible degree of the polynomial whose graph we see here. Now remember that the degree of the polynomial limits the number of zeros and turning points. So this graph has 1, 2, 3 zeros, which tells me that it has to be at least a third degree polynomial. But notice that this graph has 1, 2, 3, 4 turning points. So, and remember, turning points can be either local maxima or minima. Any place where my function changes direction, vertically speaking. And recall that the degree is always at least one more than the number of turning points. So if my polynomial has degree n, it can have at most n minus 1 turning points. So since this has 4 turning points, that tells me that this has to be at least a 5th degree polynomial. The smallest possible degree that this function could have is 5. Now, what would the sign of the polynomial's leading coefficient have to be? Well, we can make that determination based on its end behavior. Here, I see my polynomial goes up to the right and down to the left, and there is only one type of function, or one criterion that causes this. In this case, we have a positive leading coefficient, and coincidentally, we also have odd degree. So that answers our third question. Is this an even or an odd degree polynomial? It has to be odd. Remember, it looks like x cubed in the long run. So it has to have an odd degree just like x cubed. We have a positive sign for our leading coefficient. In other words, the constant out in front, the constant tacked onto that leading term, must be positive. And we have a degree that is odd and at least 5. So just from the graph, we know quite a bit about this polynomial. We won't be able to come up with an equation because we don't actually have any data points. This graph has no scale for us to base anything else off of. But we can answer questions along these lines. So in a similar vein to that problem we just looked at, we can consider a graph. This time we do have some tick marks to base everything off of. And I would like to find an equation for the pictured polynomial. Now I have just made up this graph. Our equation may not actually fit it, but we are going to do our best, and then you can toss that function that you find in the calculator and make sure that it does everything that this graph does. So the first thing that I notice about this is it has a y-intercept at 0, 8. So we can pretty much work backwards from the graph in the same way that we graph based on the equation of the polynomial. Alright, so I can immediately tell where the y-intercept is. I can also immediately pick out the end behavior. So the end behavior goes up to the left and down to the right, which only happens in one case. This happens when we have a negative leading coefficient and odd degree. So we might have a -2 as a leading coefficient, or a -1, or a -3, or a -1/2, we don't know yet. And our polynomial will ultimately have odd degrees, so our leading term might be a cubic, or a 5th power, or a 7th power. Now I can look at the number of turning points. I see 1, 2, 3, 4 turning points. So I think that our degree is going to have to be at least 5. Alright, so 5 or 7 or 9, those are the degrees that we can expect from this guy. Now this is where we start using some more powerful information. We have zeros that we can pick out at x equals -2. That's our first x-intercept there on the x-axis. X equals 1 is next up as we read from left to right, and finally x equals 4. Now the factor theorem tells me that if each of these is a 0, then there's a factor associated with it. X plus 2 must be a factor, as must x minus 1 and x minus 4. So my polynomial is coming together. I have f of x equals, I know at least a factor of x plus 2, a factor of x minus 1, and a factor of x minus 4. Now if I multiplied this all out, I would have a 3rd degree polynomial. So there must be some powers involved. The other problem is that while zeros are very helpful, and they tell me a lot about the factors of the polynomial, they don't tell me anything about a constant out front. So I might have some coefficient out in front, just like with our quadratics and just like with our exponential functions. We always want to account for the possibility of a vertical stretch, and in fact account for a vertical flip as well. Alright, so we know one more thing, looking at the graph and looking at these zeros in particular. I know my graph bounces at x equals -2. I see that it also bounces at x equals 1, and then it crosses at x equals 4, which tells me my multiplicities must be even for the first 0, even for the second 0, and odd for the third 0. So, at the very least, I need a power of 2 on both of these factors that have zeros with even multiplicity. Now, I am okay keeping this power as a 1, because at this point, my polynomial does everything it should at its zeros. It bounces at x equals -2, it bounces at x equals 1, and it crosses at x equals 4. So the only thing left to decide is what is this coefficient. And that is where our y-intercept comes in and saves the day. We know that f of 0 can be written as 0 plus 2 squared, 0 minus 1 squared, 0 plus 4. And this is supposed to be equal to 8, based on this point. So, we can crunch the numbers and solve for a. So 2 squared would give me 4, -1 squared would give me 1, and 4, oh, I'm sorry, that should be minus, not plus, I don't know where that came from. Minus 4 is going to stay exactly as it is. So a times -16, and if I divide both sides of this by 16, I see that a equals -8/16. In other words, -1/2. So finally, we come up with a polynomial to go with this function, f of x equals -1/2 x plus 2 squared, x minus 1 squared, x minus 4. And this is a 5th degree polynomial. If you don't believe me, you can do that trick of multiplying the leading terms by their powers acting on them, and you'll see this is a negative leading coefficient, -1/2, and an x to the 5th. So this satisfies our end behavior, and our zeros are happy, and our y-intercept is satisfied, as is the